Okay, so for the first question, it asks for definitions and simple properties of example of stochastic process. For Poisson process, the number of from T1, T2 of points T1, Ti in interval T1 to T2 of length T is a Poisson random variable with parameter lambda T equals to the probability of K equals to e to the power of negative lambda T times the lambda T to the power of K over K factorial. If T1 and to T2 and T3 to T4 are non-overlapping, then the random variable NT1 to T2 and NT3 to T4 are independent. So at a time moment t, there is no more than one Poisson point using point t. Using point t1, we form a stochastic process xt equals to n0 to t. And the mean of expected value of xt equals to lambda t. And the autocorrelation is rt1 t2 equals to lambda squared t1 t2 plus lambda minimum of t1 t2. Autocovariance is lambda squared t1 t2 plus lambda minimum t1 t2 minus lambda t1 times lambda t2, which equals to lambda minimum of T1, T2. And Poisson increment process is defined as yt equals to xt plus lambda minus xt over lambda, where xt is a Poisson process, and the first order probability mass p y t n over lambda equals to e to the power of negative lambda times delta times lambda e to the power of n over n factorial. And the expected value of yt equals to lambda. And autocorrelation is rt1, t2. When t1 minus t2 absolute value is greater than lambda, it is greater than delta, it's lambda squared. And if it is smaller than delta, then it is lambda squared plus lambda over delta minus lambda times t1 minus t2 absolute value over lambda squared or over delta. And the covariance, the covariance t1 and t2 equals to 0 when t1 minus t2 absolute value is greater than delta, and if it is smaller than delta, then it is equals to lambda over delta minus lambda t1 and minus t2 absolute value over delta square. For point impulse, the expected value is lambda, and the autocorrelation is rt1 t2 equals to lambda squared times lambda delta t1 minus t2, and autocovariance is covariance t1 t2 equals to lambda delta t1 minus t2. And the semi-random telegraph signal is Pn t1 t2 equals to k and e to the power of negative lambda t to the power of n to the power of k over k factorial, and xt equals to 1, k is even in 0 t, and -1 if k is odd in 0 t. And the first order probability math function is pxt equals to 1 equals to e to the power of negative lambda t, and lambda t e to the power of lambda t plus e to the power of lambda t over 2. And the mean value of expected value of xt equals to e to the power of -2 times lambda t. And the autocorrelation of lambda correlation RT1, T2 equals to e to the power of -2 lambda times T1 minus T2 absolute value, and autocovariance T1, T2 equals to e to the power of -2 lambda to the power of T1 minus T2 minus e to the power of -2 lambda T1 plus T2. And the random telegraph signal is yt equals to alpha axt, probability a equals to 1, and probability a equals to -1 equals to 1/2. Along xt is a semi-random telegraph signal. The first order probability math is 1/2. And the mean is expected value of yt equals to 0. Autocorrelation equals to e to the power of -2 lambda times T1 minus T2, the absolute value. And autocovariance is equals to e to the power of -2 lambda T1 minus T2. And for random walk, the example is tossing a coin, and the mean value is 0, and autocorrelation is minimum value of n and m times s. And the autocovariance is expected value of xt1 times xt2 equals to minimum of n and m times s. And the winner process, the expected value is 0, and autocorrelation is minimum value of T1, T2, which is alpha, and the covariance is minimum of T1, T2 times alpha. And the first order density function is this.